All right. Thank you, everyone, for joining us. This is the second day of Virus Bulletin in the red track. And for our third presentation, we're going to be hearing from Vadim Kotov of Bromium to speak about optimized malops, hack the ad network like a boss. Everyone, please join me in welcoming Vadim.
Good morning, everyone, and thanks for coming. My name is Vadim Kotov. I'm a security researcher at Bromium, and this talk is all about malvertising. So that's an agenda. I'll talk about what is malvertising, how it works, and why this problem is still prevalent. I'm going to describe inner workings of malicious flash banners, and then I'll show a demo. I'll show our approach for hiding malicious JavaScript code in a banner. Before a couple of words, here we are. We called Bromium Labs. We're a small research group in Bromium, and our interests are virtualization, malware analysis, and all sorts of security research on both offensive and defensive sides. So what is malvertising? Let's look at the typical malvertising scenario. It obviously involves a website with ads on it and an advertiser. And an attacker would like to submit a malicious banner to an advertiser. Typically, there's an approval procedure that includes security checks, but it's quite tricky to find hidden malicious code in ads, so sometimes they pass through. Then a user will visit a website which, upon visit, will send some metadata to an advertiser that might include language, operating system, maybe some bits of the search history, and so forth. Based on that metadata, advertiser picks a banner from their pool and then returns it. And under some circumstances, this might be a malicious banner. And what malicious banners typically do, they place an invisible redirect on the page that sends user to a drive-by and load attack. Over the past couple of months, we observed a number of incidents. These are just the biggest ones. For instance, Square.com is a very popular Chinese travel website. Dictionary.com and Answers.com are, they hold high positions in Alexa ratings. And Yahoo.com, well, everybody knows that, it's pretty big. So why is it still prevalent? Because this problem is fairly old, and it has been around for quite some time. First of all, volumes of advertising are so high that it is impossible to check all of them. Most banners written in something like Flash or Silverlight, and this type of rich media content is so powerful that it's really easy to hide, obfuscate, and execute the malicious code and bypass the security checks. An overall dynamic nature of web advertising makes it a challenge to pinpoint the source of attack. In fact, the character of, or the nature of web advertising is pretty much random. We got into this topic after one of our guys captured some malcode from YouTube. And as we later discovered, it came from the DoubleClick ad network. It was a malicious flash banner that redirected users to a Styx exploit kit and then served something like Zeus Trojan, if I remember it correctly. Now, after that, we were curious what are volumes of malware on YouTube, and so we started collecting Google Safe Browsing diagnostics for YouTube. It's by no means representative statistics because each entry is basically a number of attacks for the past 90 days, but still is a good rough estimate to at least have some idea what volumes are we dealing with. So on this plot, you can see the percent of malicious pages among all the YouTube pages. The good news is that the trend is in decline, and another good news is that it's actually much less than 1%. However, how many pages are there on YouTube? Probably millions, And if you just get the actual number, it still results in thousands of malicious pages. So this plot here shows a number of different kinds of malcode found on YouTube. And what's interesting here is that the number of Trojans actually is much, much bigger than the number of scripting exploits or exploits. Now, since it's not statistically representative data, it's really hard to interpret. Why is that? But one conjecture we could make is that Google engine probably detects, in most cases, detects malcode after Trojan was dropped. This on its turn might indicate that exploit kits evolved really fast in terms of obfuscation and detection evasion. And that's pretty much in line with what we observe on black markets. But it's just a conjecture. So let's have a look at current drive-by and load kind of infrastructure. And first thing to keep in mind here is that malware is a service these days. In order to infect users, you don't have to be a developer and you don't have to actually own any tools. It usually starts from buying a malware executable. It might be a banking Trojan or a remote access tool, depending on your purposes. Then having a malware executable, you might want to then make it as stealthy as possible. And what you can do is you can use one of the obfuscation services. So you basically submit a malicious sample, and then you get the obfuscated one back. Either attackers themselves or obfuscation providers, they might want to check their obfuscation algorithms against some sort of equivalent of some sort of black market equivalent of VirusTotal that checks the binary against a number of AVs and HIPs. After that, you'd want to rent an exploit kit. About 2-3 years ago, exploit kits were sold in form of server-side scripts, and in most cases, you could actually look up the source code. Sometimes they were protected with something like Zen, but that was rare. That was pretty rare. However, in this case, they'd leak all the time, so now they're leasing them. And if you captured some like IP addresses or domain names pointing at a malicious server, it usually doesn't mean that this server belongs to the person behind the attack. It actually might be like rented. So you arm your exploit kit with malicious binary. And the final step here, what you need is users to infect. You need to buy some traffic. And the success rate of exploit kits actually is all about traffic, because most kits usually serve public exploits. 0 days are rarely the case, and in fact, the majority of kits, like the modern exploit kits, are pretty much the same. They have a couple of Java vulnerabilities, probably one of the latest IE vulnerabilities. The differences are more on user interface side, obfuscation side, the way they clean their kits, like they update obfuscation schemes and so on and so forth. And yeah, so the efficiency of exploit kit depends on how vulnerable user machines are. So in this case, attackers would want to find websites with high share of unpatched visitors. And there are many other constraints, such as language, country, and operating system, and so forth. But in classic watering hole scenario, you cannot control these parameters because you basically deal with whatever you were able to compromise. But there's another viewpoint on this problem. You can pay for ads instead of paying for traffic because you pay for traffic anyway. And there are industry giants such as Google and Yahoo. They have pretty decent security level, and there are just like there are very few malicious pages on their websites. However, there are thousands more advertisers with much more charitable conditions, and they all have pretty extensive targeting criteria, such as country, language, bits of search history, and You could specify, for instance, you could specify disabling user account control in Windows as your targeting criteria. And there's a good chance that you'll get a reasonable amount of people with the user account control disabled. Because indeed, user account control might become quite annoying. And again, malicious banners are written in Flash or Silverlight, but you still have access to JavaScript. And if you have some malicious code snippets that you'd like to put there, you can do that. So before moving further, let's discuss a little bit the Flash platforms. A very, very brief introduction. I'm pretty sure that most of you are familiar with that. Flash platform is basically an interpreter called ActionScript Virtual Machine. It's used in multimedia, animation, and games, and obviously in advertising. It's 100% object-oriented, so everything is a class there, and in this respect, it looks like Java pretty much. And here are some important classes that we need to know about. External interface, a class that allows you calling JavaScript functions on the web page. Byte array is a class that allows you manipulating raw data, and it's actually a very good container for your shellcode. Loader is a class that allows you downloading other Flash clips and images from URL or render them directly from raw bytes, from byte array to be precise. And bitmap data gives you full control over image file. So let's look at the malicious banner workflow. It obviously starts on the HTML page where the ad is displayed. It gets embedded on the page. Then perhaps some parameters are passed. There's a parameter called flashvars that you can send variables to the Flash clip. It might be a URL, some bit of user information, or what have you. So first thing a malicious Flash banner would do is to check the attack triggering condition. It might be date, it might be time, it might be a URL that was submitted from HTML. Then what it does, it tries to fingerprint the operating system and the browser, and it's usually done via external interface call to JavaScript's navigator and its user agent property. And finally, it deobfuscates the payload and launches the JavaScript code. So how external interface work is a fairly small class. It has one important property and two important methods. We're going to talk about just a property and a method. Available is a property that allows you to check whether you have JavaScript calls enabled and whether the browser supports them and whether they are enabled or not. Unfortunately, most of advertisers require this to be enabled because they not just display a banner, they also collect statistics about clicks, some user information, the topics of the websites, and so forth. And then important function is a call. Call allows you to call a predefined JavaScript function on the web page. However, interesting thing here is that you can actually directly call a function upon declaration. So this means that you can basically execute any random JavaScript code on any random web page. Well, that's quite convenient. And thus, the general approach is hide your malicious code somewhere in SWF and run it using external interface. All right. So as I said, you hide your code somewhere in the Flash clip. And what they usually do, they hide it as embedded binary data. So you can embed any kind of binary data in your Flash clip. It can be anything. It can be an executable file. It can be an image. And all you need to do is you need to define this class. This class inherits byte array. Byte array, let me remind you, allows you accessing raw bytes. And when you create an instance of this class in your code, you basically have access to your bytes, and you can do anything. In this sample we found in the wild, it performs simple XOR-based deobfuscation. It has a 4-byte key. And then, using the loader class, it renders another SWF from the raw bytes. It's basically SWF inside SWF, which is normal. It's okay, but it's a good way to hide your malicious code. So, what we could do about it is we could introduce a policy that forbids any embedded data, any high entropy content, anything that looks suspicious. But even with this, there's a way to sneak malcode in the banner. And we think the most appropriate way would be use steganography, and that is hiding your code in an image. First of all, images is what ads made of. So they definitely are not checked. Or if you check them, then you need to check all the images, which might be quite resource expensive. Furthermore, most of the image formats used these days, such as JPEG, PNG, are compressed. So it's impossible to detect pixel manipulation. And so what we offer to do is we offer to hide the JavaScript code bit by bit in pixel color values, and that's it. So here's the JavaScript snippet we're going to hide. It's a simple function that creates an iframe, makes it hidden, points it to the malicious web page, and adds to the document body. And the workflow goes like this. We load a PNG to the Flash movie. Then we extract JavaScript using bitmap data. And then we execute it via external interface. And this will redirect users to Java exploit. So let me demo it real quick. So first of all, here's our image. I'm not sure you can see it. How about that? No. Yeah. Here's our image. It's a random image. It could be anything. It's a random PNG image. And here is our Python script to let me just quickly try it. Okay, nice. Sorry about that. So here's our Python script that prepares the image. What we do, we use Python image library. Here's our code snippet that we're going to hide. We append our code snippet. We append this plus character, is basically a terminating character, so that we know that this is the end of the payload. Then we walk our image bit by bit, and pixel by pixel, and hide our image bit by bit in the least significant bits of red channel. That's a very simple, very basic approach to hide secret message in an image. Then let's switch to the client side. So here's our Flash code, and here what we do, we first load our PNG, and you don't have to load it actually, it can be embedded in the page. It's just one way to do it. Then when the load is complete, we do this little typecast. We cast it to bitmap, and then we can access the bitmap data property, and the resulting object will allow us to walk, to traverse pixels, to walk all the pixels. And then we basically apply the procedure in reverse order. We extract least significant bit and compose image. Once we hit the plus sign, we create a timer. We make 3 seconds timeout, and on the timeout, we do the call. And we have a Java exploit here on the Metasploit console. And let me show you how it looks like in the wild. So here's our page, looks normal. Here's the Metasploit console. It starts sending the exploit, and you get your calc. The idea is that this is completely seamless for the user. You don't see any redirects or anything. So two things to keep in mind here. First of all, there's of course a science called Steganalysis that basically what they do, they research, they devise algorithms to uncover secret messages in images, audio files, and other types of containers. And there they have a number of impressive approaches to do that, but applying it at scale and in automated fashion might be a challenge. And then again, since these are compressed formats, there's no way you can detect picture manipulation by eye or by frequency analysis, because they are compressed, and what you'll see is just high entropy data. So what should we do about it? How do we protect from it? Well, obviously the most secure solution will be quit using internet, but for obvious reason that's not applicable. Another approach is using ad blocking tools, but there are 2 problems. First, not everything can be blocked, and secondly, if you imagine for a second that everybody starts using ad blocking tools, then what will happen, in our opinion, is ads become more complex. They become more sophisticated, and they'll bypass the blocks, and basically will achieve nothing. Another thing, we could block untrusted advertisers. Will that include blocking Yahoo and Google? I doubt so. I guess somewhat good news is that it's still drive-by and load. The main problem is still drive-by and load. So perhaps if we focus on that instead of early redirects, then this approach might result effective or efficient. So the conclusion. The most important thing, online ads are an integral part of web economy, and they're not going anywhere, and we just have to deal with them. Black market goals are maximizing profits while minimizing efforts. And malvertising is pretty much in line, it's very much in line with these incentives. So, okay, malware and ads, brilliant. What difference does it make then? You see, the traditional approach to this problem is that, yes, you can run into malware, and you can run into malware pretty much anywhere. However, we still can crawl the web and blacklist malicious web pages, and Google Safe Browsing is a good example. But that's the traditional approach. Now, if the prevalence of malvertising increases, then this approach will not work anymore, because malware will be everywhere then. Even reputable websites can sometimes serve malcode. So this, I'm afraid, there's no easy answer to this problem, I'm afraid, and this is a challenge that we have to take. And we think that ad publishers and security providers need to share their responsibility. So finally, here's some references I threw in here. Obviously, I won't read them, but when the slides become available, you can download them and check them out. They're all free access. They have pretty good cover of the problem of malvertising. And that's it. Thank you for listening. And if you have any questions, I'd be happy to answer.